Last but not least, we have Simon Duke from UW-CSC. He did his PhD at CMU, his postdoc at Princeton, and he's worked on a number of foundational questions about deep learning theory, representation learning, reinforcement learning, won a number of awards, Career, Sloan, Schmidt AI Award, and please take it away, Simon.
All right, thanks for the introduction, and it's nice to see you all. So today I'm going to talk about a classical problem, learning Gaussian mixtures with a classical algorithm, EM, or expectation maximization, and basically we show it actually works. It's a joint work with Mo, who's my postdoc, Wei Hang Xu, my PhD student, and Mariam. Mo and Wei Hang, they are both co-advised by Mariam and myself. All right, so let's get into it. So this talk is about learning Gaussian mixture models. I think everyone here knows about it. It's a very fundamental generative model, widely used in modeling, especially multimodal data. And to learn this model, arguably, the most popular algorithms are expectation maximization algorithm, or EM for short, or a variant of it like gradient EM. I'll give you precise formulas later, but these are arguably the most popular algorithm to learn Gaussian mixture models. Okay, so let's get into the detail. So here we consider the ground. Let's say we have a ground truth Gaussian mixture model with M component. Okay. So the density function, you can write it in this way. So say I from 1 to m, and then pi I star is a mixing weight. And then we have this phi mu I star x. So mu I star is the mean of the i's Gaussian component. X is some any point. And then phi mu I star x, in notation-wise, is just this Gaussian density function. We're here for, we only consider the identity covariance case, the simplest case. Okay? And then we have this pi star, they sum to 1, they are the mixing weights. So that's a ground truth model, and we can, let's say we have some samples from it. Our learning model, you can see here we use a different notation n rather than m. So here we do allow like different number of components from the ground truth. But we have the same format. We have, say, I from 1 to n, pi I and phi mu I x. Okay, so this is our learning model. Basically here, we want to fit mu i's and pi i's. Okay, so mu i's and pi i's, they are the learning models. Okay. So here our goal is to recover the ground truth P star, which is the ground truth Gaussian mixture model, something like this. Here in this talk, this red stars, they are the ground truth Gaussian mean, and this blue crosses, they are our learning means. So here you can see n may not equal to m, and we call n is bigger than m. We call it over-parameterization because we have more parameters than necessary to learn this ground truth Gaussian mixture model. Okay, and when n equals to m, we call it exact parameterization. Okay, so now let's talk about EM. So here's our model on the top, and it's an iterative algorithm. Let's say you have some initialization for the E step. Basically, it's you just compute a membership or membership width for each data point. Let's say for a data point x, okay, we compute the probability that it is actually sampled from the i's component. Okay, i's Gaussian component. So in the numerator, we have these. So this is at the tth iteration. In the denominator, we have this total probability, and then in the numerator, we have the weight, corresponding weight for the i's component. That is x is sampled from the i's Gaussian component. So now we have the assigned weights for all the data. And then given this assigned weights, we update both pi and mu through this Q function. Basically, we fix this membership function, and then we try to run maximize likelihood over both pi and mu. Here, you can directly solve this optimization problem, or you can just run one step of gradient to update your pi and mu. So that's the gradient variant of the EM algorithm. Okay. All right. So actually, there's a line of work on this topic. And for example, the first line is by Siva here. And Martin Monroe and Bin Yu, they show that this is what we call exact parameterization setting, and both m and n equals to 2. So we want to learn a 2-mixture Gaussian, and your model is also 2 Gaussians. They show a local convergence analysis kind of using the convex analysis. And then by Daniel et al., and there's some other work, they also study this m equals to n equals to 2 case. But different from Siva's work, where Siva's work, you need to have somehow a good initialization that your mu is already close to the ground truth. In this Daniel's work and a couple of others' work, they show that you can do a random initialization of the mu's or the means, and then you just run EM. You can convert to the recovered ground truth. Okay. And then there's a couple in the third line. People have shown that if you have good initialization of your learning means, then locally, then you can actually convert to ground truth just by running the EM algorithm. Okay, that's the third line. And then the fourth line is actually something on over-parameterization. Okay, so the ground truth is only a single Gaussian, and then if you have but you suppose you don't know that, but you want to use 2 Gaussians to fit this ground truth 1 Gaussian. It's still a highly non-trivial problem to analyze. And then there's a fourth line's work. Fourth line. These 2 works show that you can still achieve global convergence. Okay, it's actually much more difficult than learning a single Gaussian, and you're using a single Gaussian to fit as well. And there's a couple of more works of over-parameterization in the local phase. For example, here you can allow m equals to 3 and equals to 2. And last year we have a work where, let's say, the ground truth is 1 single Gaussian, but we have arbitrary number of Gaussians. We can establish a global convergence. This is by Wei Hang, my student, and Mariam, and myself. And the second to the last line I want to mention is also by Siva, and then Qijin, Yuchen Zhang, Bin Yu, and et al. They show that this is actually a negative result. Okay? They show something negative about exact parameterization when the ground truths have 3 Gaussians or more. Okay? So they construct examples showing that if the ground truths have 3 Gaussians, okay, and your model also have, say, 3 Gaussian, and then you do random initialization, then we'll stuck at some local minimum. So you cannot, or with high probability, you cannot recover the ground truth. If you just run random initialize EM or gradient EM, you're stuck at some local minimum. So this is like a algorithmic optimization negative result. They show that if m equals to n equals or bigger than 3, then there exists some local minimum, and you do, with high probability, convert to that local, spurious local minimum. Okay? So this shows some negative result. Okay? So here, and this is this one. This is by Siva et al. And here, our result is this last line. Okay? We show the power of over-parameterization. So here, let's say ground truth m is arbitrary. But here, if our learning model's number of Gaussians, n, is bigger than, or in the scale of m log m, you can recognize it's something related to coupon collector. That's why we have this m log m term here. Then actually we can establish a global convergence from random initialization. And then you just run gradient EM, you can recover the ground truth probability distribution. Okay, so that's our main result. So here, basically this verifies a kind of long-standing folklore. In the literature, the over-parameterization, like n bigger than m, improve this optimization landscape and enables this EM or gradient EM to convert globally to the ground truth Gaussian mixture model. For example, this paper by So enjoy the Skupta and Leonard Schumann. They study a variant of EM, like two-round EM. They show that you can, with enough separation and several conditions, with some truncation method, but they show some why over-optimization can be useful. It's related to coupon collector as well. Okay. So here, our result is the first rigorous analysis and the proof for general n bigger than m, from randomization to and conversion to the ground truth if you have enough samples. Okay. Any question about the result we have? Yeah.
In the prior work, how does the suboptimal different local convergence result?
Suboptimal here, it's a negative result, basically showing if you have, if you do randomization, then you're stuck at some local minimum. You're not recovering the ground truth. Whereas the local here means if you start from good initialization, you can actually recover the ground truth. Yeah.
So can you comment on your separation conditions?
Yeah, I'll talk about the separation condition later in our reception. It's just generally much worse or much stronger than what is actually needed if you do not use EM, let's say use SOS or those kind of algorithms.
Nothing is needed.
Sorry?
No separation is needed for the problem that you solve, right? You're not doing parameter estimation, you're doing density estimation, right? So you don't need any separation. Information theoretically, you don't need any separation.
Yeah, exactly. Yeah. So here we just want to study why this particular algorithm works. It's not about getting a better dependency or something. Yeah. Any other questions? Yeah.
This seems to appear the double descent because when n equals n, the form is optimal, suboptimal, and then when it's over-parameterized, it gets better.
It's getting better in terms of the optimization perspective. You will avoid local minimum and convert to global minimum. Yeah. So you're asking a double descent? Double descent is more on the approximation theory and the statistical side, right? This is on the over-parameterization's optimization's benefit. Cool. Any other question?
I mean, there would be double descent as you keep increasing n, right? Because would it?
So here, because we assume a ground truth Gaussian mixture, so as long as you convert to global minimum, your loss is 0. So let's say this. And here, we mainly study the optimization aspect. So we basically study the infinite sample regime.
No, but I guess as you increase n, and if you run the optimization, I guess it would be monotonic, right? I mean, how well do you approximate?
Yeah, that's true. Sure. Yeah, any other questions? Cool. All right, so now let's get into more technical details. So here's the ground truth, P star, and here's our learning model. So first, general observation is that if you apply gradient EM, it's basically equivalent to apply gradient descent on the KL divergence between P star and P. Let's say from here, I'll basically assume we have infinite number of samples and only focus on the optimization aspect. Okay, so here the specific algorithm we analyze. Here we just do random initialization. So the initialization for each mu I, we just randomly sample from the ground truth. So if you have finite samples, it's equivalently of just randomly selecting, say, n samples. We use those samples as the initialization. And here, let's say we have infinite many samples. So equivalently, we can say the initialization is sampled from this distribution. Okay, so we have n mu's, that's our initialization. And then we have the mixing weights pi I. We have n components, and each we just initialize as 1 over n. Okay. So to update pi and mu, we just fix mu and then optimize pi. So this is actually a convex program. So we assume that we just solve it. And then for mu, we just apply one step of gradient descent on mu with a fixed pi. Okay, So it's a, one variant of gradient EM. So pi's update is convex. You can view this problem, this algorithm as you have a infinitely larger step size somehow for pi and a smaller step size for mu to mimic this update. Okay. All right. So here's our assumptions. First of all, I will say these are fairly strong, and we believe there are many ways we can improve it. But let me just, for preciseness, we state the algorithm, the assumptions here. So first of all, we assume, so just for simplicity, this can be relaxed in our paper. The pi star and the maximum of pi star and minimum of pi star, the ratio of them is in the order of 1. Okay, this can be relaxed. If you have other ratio, then the number or the amount of over-parameterization will depend on this ratio. Okay, but for simplicity, let's assume it's theta 1. And then here's our assumptions. Okay, first of all, we assume this mu I stars. If you just view them as a matrix, this matrix is full rank or linearly independent. This is for, again, it's definitely for technical reasons, and actually you don't need it in practice, or I believe in theory you don't need it as well. But here for technical reasons we do need it because it's related to, we kind of reduce the problem to some of mass of moments, and there we use some property of this linear independence. Yeah, in our bound we have a dependence on the condition number, yes. And then we also have a bound. We assume there's like some regularity condition like mu I star, they're upper and lower bounded. Also, we have this separation condition, which is, again, very strong. It's a square root of D, and just learning a mixture of Gaussian in the exact parameterization case, you need like a square root of log k. So it's definitely much stronger. And this is an open question how to further relax it, or it's also possible that there's a fundamental problem with EM that you cannot learn the ground truth with a small separation. But basically, in this work, we show that with this kind of strong assumption on the separation and other conditions, EM or gradient EM does work. Yeah?
So the autonomy of mu i's are also will D.
Mu i's? I mean, it depends on how you initialize.
If you sample them, like they're
if you sample them, for example, from some, like in the Bayesian setting or some prior.
It's centered. If you like,
Sorry?
we assume they're centered, or they're all D, okay? Or it's fine.
Yeah. So it's one case that satisfies these conditions are the kind of Bayesian setting. You have some each mu I also sample from some Gaussian with some delta, and then if you delta is sufficiently large, then it will satisfy these kind of conditions. Okay, so with these assumptions, here's our main results. If n is m log m, and you have used a small enough step size eta, then gradients then converge globally to p star with high probability over the initialization at a polynomial rate. So it's not linear convergence like in the exact parameterization case. Here is a sublinear rate. And in simulation, we do see this is unavoidable in the over-translation case. I'll show you later on some simulations. So this is the first global convergence for learning Gaussian mixture models for m bigger than 2 with a gradient EM. And then if you do want to get some sample complexity, there's a simple trick to get that. Like if in each iteration you use some fresh samples, you estimate the gradient, and then you have independence at every iteration, so you can get some. And because it's a polynomial convergence rate, so in total you still have a polynomial number of samples to learn it. Well, of course, our current bound is not tight, so another open problem or direction is to study the tight sample complexity of EM algorithm. And I want to contrast this with the negative result by Chijin et al., where they show that there exists a well-separated Gaussian mixture that EM fails to convert at global minimum. So this does show contrasting with our positive result. Here we do see the power of over-translation. Like over-translation does help you to convert to a global minimum under this set of conditions.
So when you are talking about the convergence, like are you looking at like a total total variation distance between like the movement and the truth, or like some other?
Basically, look at the tail divergence, the loss,
Okay.
basically. Yeah.
This implies.
All right, so here, let me first discuss why over-parameterization helps. It's basically the coupon collector intuition. And let's say the separation is large enough. Okay, so basically, under random initialization, with this initialization, okay, then just by coupon collector kind of idea, then you can show that for each cluster L, remember we have in total M clusters, there are at least one mu I is sampled from this ground truth distribution, such that mu I minus mu L star, this is the ground truth mean, so in two norms is smaller than square root of D. Okay, so this is intuition. Let's say we have three components like this. If you have say m log m in the order of m log m Gaussians, then for each ground truth right star, you at least have one initialization that is close in the sense like in this is smaller than square root of D, close to this right star. Okay, so this is like a coupon collector. So this is actually failing case. So here you have say two initializations that are close to this mean. One initialization close, let's say, to this mean, and here this is far away from these three. So in this case, actually, if you run a simulation, you will get that it will stuck at some local minimum. In the case where this is called there's a paper called this phenomenon called one fits many. So basically, this one because it's close to both this mean and this mean here. So it will stuck on here, and this this mu will not move by much if you run simulation. You get some phenomenon like this. So this is actually a failure case. But if you have, for each ground truth mean you have one mu that's close to it, then eventually it will learn the ground truth. Okay. Another aspect, which is actually different from prior work. In many prior work, they don't actually update the pi. Because in the exact parameterization, they just set the pi to be the ground truth, or just one, all of them are 1 over m. But here, because we are in the over-parameterization regime, we do need to update this pi. Okay? So for example, this pi for this one, it may convert to 0 if it does not convert to any of the ground truths. Okay, so this is actually one phenomenon we observe. You can observe in simulation as well. Okay, so here's, let me illustrate this a bit more. Okay, so the first figure is we compare exact parameterization with over-parameterization. So for the blue curve, we have ground truth have 5 components, and we also have 5 components that actually stuck at some local minimum, like here. You can see the loss is pretty large here. And then if you do over-parameterization, the loss decreases. To correspond to this orange and the green curve, they keep decreasing, and they will converge to the global minimum eventually. Okay, so that's a loss, and you can see here this is not a linear convergence; it's actually a sublinear convergence as well. Okay, so now let's look at the middle figure. This is the exact parameterization case. Again, the right stars, they are the ground truth, and the crosses, they are our learning means. You can see here, for some ground truths, we do have convergence. For example, this one converts to ground truth. This one converts to the ground truth as well. But for some others, it may not convert to the ground truth. For example, for this ground truth, there's no mu that converts to this ground truth. So this is a failure case where we do not recover the ground truth Gaussian mixture. Okay, and for this one, this is an over-parameterization case, n equals to 10. For you can see for each ground truth right star, there are at least one mean crosses, at least one cross that converge to the ground truth. For instance, this one, this one, this one, this one, this one. Okay, and you can also observe there are some means that do not converge to any ground truth, like this one, this one. Okay. So they do not converge to ground truth. their corresponding pi, their mixing weight, will converge to 0. Okay? So actually, we have this if-else condition, like either eventually you convert to ground truth, or your mixing weight will be 0. Okay, so that's what we can observe. I have like 15 minutes left. Here I'll discuss the main technical challenges, but the main ideas are from the previous slides. Any more questions? Yeah.
If I don't care about like m I over parameters more, can we like relax the assumption, or like probably if like the number of n's scales with d, then like square d would be relaxing the initialization at this.
I think m log m is kind of necessary because it's coupon collector problem. So you need, with high probability, it has at least one mean for one ground truth mean. And your question is, we can relax it, or?
No, like make it larger and like n scale with md, but like relaxing the separation assumption.
Oh, I see. That's yeah, that's possible. I think we don't have a. Although I think our current proof cannot go through, but yeah, but I think that's possible. And probably our current, I would say our current condition on separations is also like stronger than needed as well. So it's I think it should be able to be tightened as well. Okay, so now let's get into some technical details. So first idea is we need to have this partition of our learning means. So you remember we have n means want to learn, and we separate them into m sets. Okay, basically for this SL, is that for all the means mu i's, such that they are the ones that are closest to mu l star compared to other means. Okay, so basically you just partition the space such that we group the means or mu i's to its closest underlying ground truth mean, mu star. Okay, so that's our partition. So you can see here, if you do over-parameterization, then with high probability, each set has at least one component. But if you do not do over-parameterization, then you may have an empty set, and so our analysis cannot get through. Okay, so there are basically two challenges that are different from prior work. One is that, like what I said, we need to update this pi, and pi may convert to 0. So this actually complicates the analysis quite a bit compared to prior work. And especially, this is something unique in over-parameterization case that pi can be 0. And secondly is what we call cross terms. It's a bit more technical, but basically in your gradient you have terms from the ground truth cluster, or you're closest to. You also have the terms that are from the other clusters. Those are what we call cross term, and they're not 0 even at the global minimum. So, but you need to find some way to handle them as well. Okay. Yeah. So these are the main two technical challenges. So here in our proof, actually have a two-stage proof. One is called global convergence. One is the local convergence. For the global convergence, we just want the loss to convert to some threshold below epsilon 0, some threshold. And then for the low convergence, we really want to convert to 0, and from epsilon 0. Okay. The overall strategy is aligned with a recent line of work on non-convex optimization, is to lower bound the gradient. So basically, this is a PL condition. If you have a gradient lower bound by the loss, like you have some form like this, then you can show the global convergence. This is a standard PL condition, and then the convergence rate depends on this polynomial. And the general idea to show this is to construct a decent direction. Let's say here, let's say we have, let's say consider the gradient with respect to mu. Let's say we need to construct a delta 1 to delta n such that this is the inner product between these decent directions and our gradient. You can show that this inner product, or the inner product between the descent direction of our gradient, is bigger than some polynomial of the loss function. Then just by implies a gradient lower bound of this form, and then we can use PL condition to show the global convergence. Okay. The key part is how do we find this delta 1 to delta n, and how do we establish a condition like this. Okay. So here's our result for the global phase. Okay. So our threshold is just like exponential of the minus separation square. Okay, so basically it's converting to the very local phase. Okay, that's our first phase target. And our result, like saying after this number of iterations, where eta is step size, you can converge to losses below this threshold. Okay, so the descent direction is actually pretty natural. Okay, it's just a distance between your mu I and the ground truth mu I star. Let's say this mu I belongs to this L, this SL, the set that's for mu L star. So the descent direction is just the difference between mu I and mu I star, and if you compute the inner product between this term and the gradient, you can show it's bigger than 1 over d or square loss square. Okay. So here we have 1 over d because it's only for global phase. In the local phase, actually we don't want any kind of this hard threshold. We only want the loss on the right hand side. But for the global phase, basically when we convert to 1 over d, we are at this threshold. Okay. All right. So yeah, so this is our goal, and basically the descent direction are this. Sorry, it's a bit small. It's this yellow lines. These are descent direction. It's a difference between our mean mu I and the ground truth, say mu L star. Okay. All right. So here's a bit more technical, but basically we can show that this is the inner product between the descent direction and the gradient. Mainly it has two terms. We call the second term the cross term. So here we have notation psi. It's just a membership function, membership width for the i's component of the particular x. So you can observe that the psi I is kind of exponentially small with respect to separation if I does not belong to, say, Sj. So the intuition is let's say, this I is far away from some ground truth mean, okay? Because we have very large separation, and because we have this Gaussian density function, it is it's a sub-Gaussian curve, so it's actually exponentially small. Okay, so now we can look at which terms have this kind of exponentially small magnitude in it. For example, here, if this j does not equal to L, okay, so if j equals to L, this equals to 0, but if j does not equal to L, then this corresponding psi k here will be exponentially small. So you can look at this term, basically the second term here, they are exponentially small. They are in the exponential of minus d squared. And similarly for the first term, if L does not equal to j, then you have some exponentially small terms. So only left with terms, at least for the global phase, you only have this term that L equals to j from the first term. So that's some simplification we can make. Okay, so to analyze that term, actually we need some techniques from Hermite polynomials. So this is a very quick introduction. For 1D case, basically this is a set of or a sequence of polynomials that are orthogonal with respect to some underlying distribution, say Gaussian. And you can, just like Fourier analysis, you can expand any function in terms of this polynomial basis with some coefficient. And the Hermite coefficient is just kind of an inner product between your function and the case polynomial from the Hermite basis. There's one useful fact is that if x is from Gaussian, and then if it, like for this evaluation, the case polynomial is actually a tensor product of mu to the power of k for multi-dimensional case. Okay, so here's our main idea. Let's look at this term here. So it's just we only consider L equals to J term from the first term in our decomposition. You can write it in this way. Okay, so I think the main takeaway from our analysis is that if you use the first two terms in Hermite polynomial expansion, where you end up with these two terms to expand this term, you have these two terms. And then you can have this inequality, and this inequality, you can use it to upper bound the loss. So I know it's a bit technical, but the main takeaway is that here, you can ignore those cross terms that are exponentially small and looking at this L equals to J's term. And for this, to analyze, to relate this to the loss, you do Hermite expansion, and then you end up with kind of related to the mean and the pi's, and you can use these to bound the loss, upper bound the loss. That's the main takeaway from our analysis. So that's the first part for the global phase. And this is for the local phase, where we do want to show that starting from some loss that are very small, and then as t goes to infinity, the loss converts to 0. So this is very different from the prior work where you have exact parameterization, where basically can show some kind of strong convexity. Here, remember, we have some phenomena that pi may convert to 0, so that it's not really strongly convex. It's not convex as well, so we need some analysis there. Okay. The descent direction, we need a finer descent direction. We only consider those mu i's that are already very close to the ground truth. Because the other, let's say we have some mu I that not in any of the SL close, so it's not close to any of the ground truth mean. For those mu i's, they will convert their corresponding mixing weight pi I will convert to 0. So that's the intuition. But here we do a final analysis. We just look at the mu i's that are already close to one of the ground truth mean. Okay. So key challenge here is how to handle the cross term. So remember, we have this term that we said is exponentially small. However, if we want to show that loss converts to 0, so even though it's exponentially small, we still need to handle them. So our idea is the following. So we do Taylor expansion of this term. So we have ended up with one ground truth term that is like only related to the ground truth, and some perturbation term that I want to show that as we apply gradient descent, this term will convert to 0. The first term is what we call the linear term. You can see here is only related to this is pi L star and mu L star, so that's pi and the mu L from the ground truth, and we want to show that within this set, the sum of pi and mu I convert to this term. So that we call a linear term. That's a first order Hermite expansion. And this, if you're in the exact parameterization, there's actually a one-to-one mapping between mu I and mu L star. But in our case, we have over-parameterization, so you have multiple I in the same SL. Okay. And we also need a second term because the pi I may convert to 0. So we need a second term to show that pi, at least in some case, pi may convert to 0. So this is what we call second term from Hermite expansion. So this is a weighted, weighted individual distance square. But you can see here is a pi times the mu I minus mu I star square. Okay, so in this case, either mu I converts to mu I star, or its corresponding pi I will convert to 0. Okay, so that's what you need to kind of exact parameterize or exactly recover the ground truth. And this show up due to over-parameterization. Okay, so these are the intuitions. I want to show these are small, and this is kind of identifiability condition that you either have pi goes to 0 or mu I convert to one of the mu L star. So this is what we call identifiability to establish this. So basically, we want to show that when losses goes to 0, then pi and mu convert to pi star or mu star, in the sense that either pi I convert to 0 or mu convert to 1 of the mu star. So the key idea, so we need some technical ideas. One is to use this test function. Okay, so we need to relate this loss to the parameter arrow we talked about. So here's we use the general idea is to use some test function g, such that square root of the test function g, upper bound, you can see here, this is basically the difference of expected value of g between p and p star, and we further relate this difference of expectation to the parameter arrow. Okay, and the parameter arrow is like what we said, is kind of identifiability condition, like the linear term converts to 0, and this quadratic term converts to 0. Okay, so how do we handle this? So KL divergence often is hard to lower bound. So here we use, I think terminology-wise, it's called homotopy method. Basically, we choose some theta to interpolate p and p star. And in our case, theta you can just choose to be 1/2. As long as the constant we can get a polynomial bound. Okay, so this is existing inequality that's very useful. You can lower bound the KL divergence. It's lower bounded by 1 minus theta log 1 or 1 minus theta, and then I can relate the loss KL divergence to something that is like quadratic, okay, which is we know is easier to handle. All right. So here, basically, we'll use this inequality. So let's say we have some test function g. We divide it by p theta and here we put the expectation over p theta. And then we use Cauchy to upper bound this term as the square root of this part and square root of g square under some p theta expectation. And here for this part, we upper bound by L. Okay, so here we use inequality like this part is upper bounded by loss if we choose theta to be some constant. Okay, and also related to some test function g under the p theta norm. But as long as theta is constant, just g theta, g's norm is upper bounded. So we have some. If you do not care about polynomial rate, then we have this square root of the loss is upper bound this difference of expectation of g over p and p star. So the main takeaway here is that this is very useful inequality. You can use it to upper bound, also lower bound KL, and when combined with test function idea, you give a very useful bound here. And secondly, how do we choose these test functions? We actually just choose define this test function to be Hermite polynomial and some basically any unitary or unit norm vector. Okay, so if we choose like test function of this form, like case Hermite polynomial and some unit vector, then with this property from Hermite polynomial, we can rewrite this difference of expectation of function g as a difference of the moment of the means and the pi star. Okay, so that's basically the main idea how we relate the loss to this. So the moment of the means and pi's. Okay, so that's the main takeaway. Like here, you can use the Hermite polynomial as a very useful tool to relate those the loss to the moments of pi and mu's. And then the rest, basically, we can use the existing idea of using method of moments to bound these terms. And this is a line of work. Using instead of using EM, but use method of moment to learn mixture of Gaussians. And there we can establish the condition or this connection between this EM and this line of work using Hermite polynomial, and we can reuse some ideas from there to establish our final bound. That's our main idea. Yeah, I think I'm over time already, so I can maybe take some questions. Yeah.
So I have a basic one. So is it the case that if you had run k-means here on this population landscape, that you would have gotten stuck at something like e to the minus delta squared or whatever? That is.
If you run k-means?
Yeah. Yeah, and then I say take I don't know how to convert it to a density, but there's probably some way to do this.
I think you can show, if you do over-parameterized, you can still get very close to the ground truth. Yeah, because in our simulation it's similar to EM, right? Instead of gradient EM. Okay.
Yeah, but I guess my question is, it's a sort of hard truncation, so you lose the Gaussian tail, and does that stop you?
Oh, I see. That's a great question. Yeah, it's possible. We didn't try that, but that's possible. Yeah.
Are there any things stopping you from using this analysis in like an under-parameterized regime, just to understand where the parameters would converge?
So some part will not go through because there will be some empty set for the SL, like in the partition, and those there's no good way to analyze. I think that's the hard part. Like you have an empty set, and how I think we can still analyze in this framework because we can analyze the interaction between different clusters. Yeah, I think we may have we maybe get some characterization of the under-parameterized case. Even the exact parameterization will fail as well. It depends on it depends on initialization then.
I'd just like to thank you all for participating on behalf of the organizers, Saeed, Bob, Marian, and myself. Thanks for coming.